So this will be the final lecture, right? Uh, now, today's lecture is really going to be about batteries, okay? But I thought that, it's important to put it in perspective that batteries really are all about storage, okay? That you store energy and then you can release it appropriately, all right? Now, let us also look at, some of the other things that we have looked at for storage. One is, of course, nature does a great job in terms of photosynthesis, the biomass that it creates, and oil seeds, and you get so much of oil. Okay, and they're all high energy products. Okay. So it's as if all that sunshine has got concentrated in some high energy products, and that's what you can then use. Okay, you can use it in different forms of fuel. Right? Or we've also seen that you can lift water, okay, to a height, all right, using maybe solar energy or some wind energy or whatever, and then later on you can use the potential energy, all right, in off-peak hours, and you can generate power. That's also a nice thing. We have also seen that you can store heat, okay, in the form of molten salts, and then use them appropriately, okay, at a right time, or even by high calorific value fuels. Then there are, of course, some chemicals which are very suitable for fuel cells. And probably the best of the lot is hydrogen. And we have discussed various ways in which hydrogen is produced. And of course, the holy grail would be to produce it using solar energy. I mean, that's very important. And then you can use it in a fuel cell along with oxygen and convert it into water and get electrical power. Then there are certain storage of chemical energy which are especially suitable for battery applications. Okay, battery uses more conventional chemicals, whereas in a sense even a fuel cell is a battery. Okay, except that you are using certain conventional fuels, like hydrogen or methane, natural gas, things like that. Okay, but otherwise they have a similarity. There are two things which I have not discussed, and probably I will not be discussing, although I should have. One is, the osmotic energy is another very important storage form, where sometimes if you are evaporating brines, they can get very very concentrated, okay, and extremely saline conditions that can be created, highly saline brines, and they have very high osmotic pressures, okay? And so they are very good for doing work, okay? So you might be able to remove water from a feed stream, using this osmotic energy of saline brines. It's also a storage. I mean, solar energy did all this work of evaporating the water, and in the process, it left a very high energy form of brine. Okay? There's another which I will not discuss, which are not so different from a battery, but a supercapacitor. Battery operates on redox reactions, which we know, whereas a supercapacitor is all about electrostatic charges. Okay, but that's again a lot of work going on in the area of supercapacitors. And then there are things like flywheels, which are spinning at extremely high RPM, very heavy stuff, and tremendous amount of kinetic energy is there in these flywheels, and you can appropriately actually harness the that energy. Okay, so this is another. Okay, so now let me come to battery, which is what I'll be focusing on in today's lecture. Now, I think it's also very important to understand the origin, of the battery rather than just saying battery is this and that. Okay, and really the origin was in when Galvani did a very famous experiment, and where he connected some wires to the leg of a dead frog. Okay, and it almost as if the frog jumped alive, and really Galvani thought that the animal had generated electricity, and he called it as animal electricity, 1780, and later on it was Volta, after whom the volt unit is named. He did a very interesting experiment where Volta replaced the frog, kept everything else the same, okay, and replaced the frog with an electrolyte solution, okay, and and found that it's actually generating current, okay, and so that was very clear that it was a current that was being generated, and it's quite clear now that it was because the frog still had probably a lot of electrolyte in it, and that completed the circuit, and so current passed, and so some muscles would have twitched, and the frog would have jumped, and so that was a huge finding, and later on, Volta also made the first battery, okay, and which was effectively taking Zn, zinc, and zinc became zinc 2 plus, and on the other side, ions, H plus, hydrogen ions were converted into hydrogen. He had taken sulfuric acid, and it was such a revolutionary thing, the generation of electricity in this manner, that Volta was given a temple as a prize. I mean, it was really considered to be extremely important. He then also went on to make what is known as the voltaic pile, and where he took two different metals, copper and zinc. By the way, what I didn't tell you is that the reason why this happened was that they found out later on that they had used two different types of clip, and the two clips were different metals, and so they were working as the anode and the cathode. If it had been the same metal, it would not have happened. Okay, and that was the good fortune, which they had, that they had used dissimilar metals. Okay? So effectively drawing on the same idea, he could take, let's say, zinc and copper. Zinc was the anode, and copper was not the cathode, but I mean copper was there, but in the electrolyte, he had copper ions, in solution, and so what happened is that copper can get very easily reduced to copper ions to copper. Okay, it's got a positive potential for that, whereas zinc actually wants to give away electrons, okay, and becomes Zn2 plus. So it is this reaction which is favorable. E0 is equal to 0.76 volt. This is the oxidation reaction, and this is the reduction reaction. Now, this is another thing, that whenever you see redox potentials, ask yourself, are you looking at the reduction potential or the oxidation potential? And write the equation in the correct way. What I prefer to do always is, write it in a way that I can add up the reactions and make the electrons disappear. Naturally, this is on the right hand side, this is on the left hand side. So they will go, and my net reaction will be Cu2 plus plus Zn goes to Cu plus Zn2 plus. Okay. So if you put it that way and write the corresponding potentials, that's the correct thing to do. You'll never go wrong. Okay, in that way. And but Volta went on to do something else. That he didn't only take one of these; he made a pile of this. And so when you make a pile, it is like putting several cells in series, and you end up generating a very high voltage. And you can also put things in parallel, which will help you to get a higher current. Okay, and he could generate cells which could generate large voltages. Okay, by this pile. Now, just to tell you that even nature does that. Like you may have heard of the electric eel, which I mean, sometimes it can give you a huge shock. The eel. Okay, and it's something similar to a voltaic pile. It has got many dish-shaped cells, which each one generates electricity, and because there are thousands and thousands of them stacked together, together it generates a very large voltage, and you can get a really bad shock from an electric eel. Okay, so that's the origin of electricity. And of course, subsequently, Michael Faraday taught us the laws of electrolysis, as you know. And what he said is that if there is a reaction taking place at the electrode electrolyte boundary, just like over here, okay, then the amount of change that takes place is proportional to the amount of current that you're passing. Okay, and the second thing is what he said is that the actual amount of chemicals that you see having changed, that will depend on the equivalent weight. Okay, like for example, if this is a two electron process, and if the atomic weight of copper is copper, the atomic weight, okay, then the equivalent weight will be to divide that by 2, and so that how much material, how many moles would you get per mole of electron. Okay, so that's really what he was trying to say in his second law. Okay, now let us try and understand a little more about batteries. Now, batteries are defined, their performance, their specifications, etc., in terms of some specific numbers. Okay, so that's what will help you to compare across the board different types of batteries. Okay, and like for example, what is the total amount of energy that is stored in a battery? Okay, that will be actually what will be watt hour, and so effectively it will be the product of the voltage and the ampere hour. Ampere times hour will give you the number of coulombs, in that, and multiplied by voltage. So I'll effectively get energy in terms of joules, and so that's what it is. Now, if for example I want to know per kilogram of weight, what is my how much energy am I going to get? This is not telling you anything about what is the size of the battery. Okay, it's just telling you there's a battery. Okay, which generates so much of voltage and so many ampere hour of current. Okay, so if you want to do that, then you divide by the weight of the battery. Okay, and effectively, it will be watt hour divided by weight per kilogram. So that is the definition of specific energy. Now, there could be certain applications where more than the weight, what matters is the volume. Like in an aeroplane, for example, the space could be limiting, all right, and of course the weight is also important. So you might also want to know what is the energy density, which is the watt hour per unit volume per meter cube. Okay, so this is per weight and this is per meter cube. Specific energy density. Then another very important thing is specific power. This is only telling you, okay, how much is the total amount of energy I can get out of a battery. But I might want to draw power very fast, like when I'm starting a car. Okay? I mean, you're just cranking it, and there's a surge of current. Huge amount of current has to flow in a very short period of time. Okay, I mean, if it only flows, very gradually, then you're not going to be able to start your car. Okay, and so what you therefore need is what is known as the specific power, Okay, obviously power means what joules per unit time. Okay, so it will be basically the power is that it will effectively be watt. We know that is joules per second is watt. Okay, so specific hour, and it will be per kilogram of battery weight. Okay, so that's what is meant by specific power. Okay, then there is also something called ampere hour efficiency. All right, so what that is like, suppose I've got a battery and I'm charging it. All right, you're putting it in the connecting it to the mains, and your battery has got 100% charge. Okay, and you can actually calculate how much was the amount of charge that you put into your battery. Okay, and then later on, when you're drawing, you're letting your battery run. Like let's say your mobile is running. One can actually calculate how much is the amount of charge that flowed out from the battery. Okay, and the two values may not be the same. Okay, so ampere hour efficiency is the percentage of the charge which I got back. Okay, that's very important. Okay, what was the percentage of the charge that I put in that I got back? Okay. Now, by the way, we'll come to this like specific energy. This is a table based on specific energy, and what you can see is this is the specific energy, okay, and this is the specific power, okay. So this is very important. This is very important, okay, and it is trying to say, it's trying to compare different types of battery and trying to see, how they stack up. And what you actually see is the lithium-ion battery performs very well on both counts. It gives you high specific power as well as high specific energy, and that's the reason why there's so much of interest in the lithium ion battery, and I will be discussing that in more detail as we go along. Okay, but specific charge is not telling you anything about the total energy, because charge is only coulomb. I put in so many coulombs of charge and I got out so many coulombs. Okay, but we know that energy is you have to multiply it by voltage. That's when you get energy. And so I might also equivalently want to know that how much energy did I put into my battery. Okay, obviously I have to know what is the voltage at which I'm putting in the charge, and what is the voltage of the charge that I'm getting out at the time that the battery is being used. Okay, so then I can get a number of energy. Okay, and energy efficiency would be that how much actual energy did I put in. Energy means how much voltage into ampere hour did I put in. Okay, and how much did I get out. Okay, now there's another very important term which is the self discharge rate. Sometimes you're not doing anything, but you leave your laptop on for or even if it's off. After some time you'll find that your battery doesn't have quite the same strength as when you shut it off. Same happens like you've gone for a vacation, and you come back and you see that you're struggling to start your car. Okay? That means what? I mean, my car wasn't running, okay, but my battery was getting drained. Okay, so that is known as the self discharge rate. Okay, even when I'm leaving it unused, these things will tend to discharge, and that's also extremely important as a parameter. Okay, and there's another which you need to know. Like if you are say running using your laptop or mobile, and if you let it drain out completely, and you say, oh, my battery, my phone is dead. Okay, and then again you are trying to charge it. Okay, now it's been found that if you let it completely drain out, and that is known as a deep cycle. Okay, I've almost let it run out to 100%, and then I'm charging it. The battery will tend to go off, much faster. Okay, and so battery life also has to take that into account, that how many such deep cycles, can you actually tolerate. Okay, and what would be the effect, how much would be the loss of efficiency if I did that too many times. Okay, so try not to do that. When your battery is still got about 30% of charge, recharge it rather than letting it drain out completely. Now, another is, in fact, just today I found out. I mean, I had to give my mobile for. I find that my battery has gone dead, and probably because the last 2 days it was a bit cold. Okay, and battery performance depends critically on ambient temperature. My phone is quite old, battery is also old. That must be the reason, and so sometimes it will suddenly fail. Okay, because of change in temperature. Okay, so ambient temperature also affects performance. As I said, the charge and discharge rate, like how quickly am I discharging? Okay, like how much power am I drawing? If I'm drawing too much power, the chances are that my battery will wear off faster. Okay, battery geometry also has a role. Okay, the method of charging, like if you try to let's say you've got a 10-volt adapter, and instead of that you use a 24-volt adapter, thinking that you will charge your battery faster. Okay, you could actually spoil it. Okay, so the charging method is also very important, and also cooling needs. Sometimes it heats up, and we'll talk about why these things happen. That sometimes if you are operating your battery, and if there is no draft of air, it can overheat, and that can affect the performance. Now, so from this, actually, you'll understand also why some of these things happen. Like when we write a battery, it's got a certain cell voltage. Okay, if it's actually got an EMF. Okay, which is the thermodynamic cell potential. But every battery will also have an internal resistance. There has to be a resistance. So what happens is that even when you're drawing power from the two terminals, and the current is passing through the battery, because of the resistance posed by the battery, okay, so there will be a voltage drop across this resistance. Okay, that is I times R. The amount of current and R. Okay? So the net voltage which I'm actually seeing, at my terminals is equal to E minus IR. I'll never get this unless my R is equal to 0, which never happens. Okay. Now, what happens is, even if my R is constant and is low, but suppose I'm drawing too much of current, okay, like very fast charging or discharging, so obviously the voltage drop across my resistor will be higher because the current will be more. So I'll end up getting a lower potential at my terminals. Okay, and therefore the performance will obviously depend on how you're drawing the current. Okay, also remember these conventions, that this is the standard convention of a battery, where we put one big line and one smaller line. You can see they put it. Okay, now the big line is typically given a positive sign, and the small line a negative sign. Now this is the negative electrode, so electrons will always flow from the negative pole to the positive pole. Okay, now earlier days, when people didn't know all these details, the conventional current, direction was always shown from positive pole to negative pole. But actually, if you look at it in terms of the flow of the electron in the external circuit, okay, it is always from the negative pole to the positive pole. You can ask me questions also. Huh? Okay, now let me, I told you that the how you draw power from a battery is very important. Like I said, if you are, starting a car, then a huge amount of current is being drawn. Okay, whereas once the car is started, and then only my, my AC is working, or the lights are working, and they're running off the battery, then I might be drawing relatively less current. Okay, so this actually was found out by this person Puchard, and so what he found, like suppose I have a battery, like let's say which has got 10 ampere hour, okay, of charge, and now 10 ampere hour means, like suppose, like let's say I say that let me draw 1 ampere, of current, okay, from my battery. Then theoretically what I would expect is that obviously it will last me for 10 hours, because 1 ampere multiplied by 10 hours, I'll get 10 ampere hour. Now, suppose, like let's say I were running it at 10 ampere, and so you might say, yeah, you're running it at 10 ampere. Yeah, I'll be able to run it for 1 hour. Then I'll also get 10 ampere hours. I multiply one by the other. That's what it'll get. But that's not what happens. Okay, and what happens is that the faster you draw the charge, means that a higher current, higher ampere, uh, the performance will go down, and you will not be able to run your or use your battery for even 1 hour. Although it says the rated capacity is 10 ampere hour. So what this person Puchard came up with was this equation, uh, and what he called it is CP, which is known as the Puchard capacity. So it is not this ampere hour capacity as we define it, but Puchard came up with his capacity as CP, and he said that it is equal to I, the current, to the power of constant K, okay, and times the time. Okay, actually T is time, T is not temperature. Okay, just make a note of it. So, suppose let's say I have a lead acid battery. Now what was found is that the K value is something like 1.2. Okay, and this K is known as the Puchard coefficient. Okay, and this is the Puchard capacity. So this is Puchard capacity, K is Puchard coefficient. Okay, now so he's just giving an example. Suppose the battery has a nominal capacity of 40 ampere hour at the 5 hour. I mean, this is just knowing the ampere hour, and I'm finding that it has got 40 ampere hour of capacity at the 5 hour rate. Okay, and what that means is that this means that it has a capacity of 40 ampere hour, which means that the current that is actually flowing, okay, will be 40 divided by 5 is equal to 8 ampere. Okay, now I know the current now. Okay, I know also the time, which is my 5 hours. Okay, so, and let's say I know the K, the Puchard coefficient for this thing. Let's say for a lead acid battery, the example is for that. Say the value is 1.2. So I'll write Cp is equal to 8 to the power 1.2 multiplied by 5 is equal to 60.6 ampere hour. So in a way, the actual capacity is 60.6 ampere hour, but you are actually getting only 40 ampere hour out of the system. That's effectively what it means. Okay, so this is where knowing the Puchard coefficient and Puchard capacity is important. I might give you small calculations to do, around this. Okay, in the exam. Okay, let's take another one. Like let's say I want to. I don't know the Puchard coefficient. Over there, I have at least taken 1.2. Because someone gave me that value. Okay. Now suppose I don't know the Puchard coefficient. Okay? But what I can know is what is the discharge behavior, let's say under two different operating conditions. Okay, something I have to know. Okay? So let's say there's a battery, and which was studied at two different discharge times. Okay, and so in one case at 42, they got 42 ampere hour at a 10-hour rating. Okay, and for example, considering that a 42 ampere hour at a 10-hour rating battery has a capacity of 33.6 ampere hour at the 1 hour rate. Okay, so this is what it is. I mean, that's So obviously, when I'm trying to run it for only 1 hour, and obviously I'm drawing a large amount of current, within that time. So these can vary. Okay. So what I can get is that you know, the I take my C1, which is the ampere hour capacity, let's say at the 10-hour rating. So basically, I put C1, let's say this is my capacity, and divided by T1. Let's say T1 is equal to 10. Okay, and I don't know I2, but I'll calculate. I2 is equal to C2 by T2. Okay, where C2 was my 33.6. The same battery gave 33.6 ampere hour. Okay, when I grew it at 1 hour rate. Okay, and so my time is basically 1 hour. T2 is 1. Okay, and then I can write this equation of Picard capacity. Okay, so Picard capacity is equal to I1 to the power k multiplied by T1. Okay, and Picard capacity here would be I2 to the power k multiplied by T2. Now Picard capacity does not change. Picard capacity would be the same. Okay, for both of this. Okay? This capacity that you are here seeing is what is known as the nominal capacity. Nominally, as people understand it, that how long am I using my battery for, and how much current did I draw. That's what nominal capacity is. That's what this is. Okay. So Picard capacity doesn't change. So I can, from this, I can therefore equate this part and this part. The RHS of the two I can equate. So I can write I1 to the power k T1 is equal to I2 to the power k T2. Okay, and then I can take the I2 over here on the left hand side, and I can write it as I1 upon I2 to the power k, and is equal to T2 upon T1. I take the T1 in the denominator on this side. Okay, and then it's not very difficult. I can take the log of this. So actually, it should be a small k. Okay, it should be so I can write it as it will be what, k log I1 upon I2 is equal to log T2 upon T1. Okay, so I can write therefore k is equal to log T2 minus log T1, because log T2 upon T1 is equal to log T2 minus log T1, and at the bottom it will similarly be log I1 minus log I2. Okay, so that will be my k. Right? Now I know the values. Okay, what was my I1? I1 was 42 ampere hour at 10-hour rating, which means that the current I1 will be equal to 42 divided by 10, which will be equal to 4.2. Okay, so I1 is equal to 4.2. And what is I2? 33.6 divided by 1. Okay, so it will be 33.6 ampere. That's what I1 will be. So I've got my values. I've got my I1 and I2 values. I know my T1 and T2 values. Okay. Okay. And so now I can write this as k is equal to log of T2. T2 is equal to what? T2 is equal to 1 this time, 1 hour. Okay. So log 1 minus what was T1? 10 minus log 10 upon I1. Okay, what is my I1? 4.2. Okay. Log 4.2 minus what is my I2? 33.6 ampere. Okay, minus log 33.6. Okay, so you can actually calculate this out. Okay, and you can see that you'll get a value of 1.107. Okay, and so I've now got my value of k. So if I know the discharge behavior at two different conditions, from that I can estimate k following this. So now I've got my k. Okay, and so I can actually put in any of these data. So I can write Cp is equal to 4.2 to the power 1.107, which is my k, multiplied by 10. So I'm just putting it into this value, okay, and it comes out equal to 49 ampere hour. Now, if you had put it in the other one, okay, which is that 33.6 to the power 1.107 multiplied by 1, okay, again that should have been equal to 49 ampere hour. Does anyone have a calculator?
Yes, sir.
You have? Okay, just do the calculation.
So it's almost like 48.9, sir.
Perfect. Okay, so now you know, okay, that the Picard capacity does not change. Okay? That is the, so you can look at the Picard capacity as a more fundamental figure, you know, and these nominal capacities, you know, whatever you get, it means nothing because it will just depend on how you're running your battery. Okay? I hope that is clear to everyone. All clear?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. And
Yes.
like for example, someone did a actual study with a lead acid battery, okay, and which had a certain performance, okay, and so using that kind of equations and all, what they did was they calculated the theoretical points, okay, and experimentally they measured what was the discharge current for different capacities of the battery, okay, and they found almost identical behavior, which means that this equation is quite a reliable equation. Okay, now what we'll come to is the two types of battery, which all of you know. One is actually known as the primary battery, and this is the ones that you dispose of. Okay, like all these remotes, typically remote for AC, this that. Once it goes bad, you put in a battery, okay, and then when it goes bad and you chuck it away, you put it in the dustbin, right? You don't you cannot recharge that. So that is a disposable non-rechargeable battery is known as a primary battery. Okay, and these are let's say two very important examples of such batteries. Okay, and one of those I'll cover, and then another, of course. Now, most of the battery what you have learned, okay, is all about these are all based on they're not solid state. The electrolyte would typically be some aqueous solution, or it will be a pasty material, but there will be some water in it. So these are all aqueous electrolyte batteries. Okay, but then Matsushita company, they made the lithium battery, which is not the lithium battery as we know it. Okay, which was it actually used non-aqueous electrolyte. There was no water. There was some other solvent which they had used. Very interesting battery. I'll talk to you talk about this. Okay? And then, of course, is the what for from the point of view of sustainability is so vitally important that you don't chuck away your battery every time it goes dead. You can recharge your battery. Okay? And of course, the greatest example of that, is and what is still the workhorse, which is used by all of us, is the lead acid battery. Okay? That's the battery that is in your car. Okay? And then the NiCad battery, the nickel cadmium battery. There's another one, nickel metal hydride. I mean, there were a whole host of different batteries which were invented, and of course the grand prize, which subsequently won the those people who made this, they got the Nobel Prize for, which is what is known as the lithium-ion battery, which is what is there in your mobile, what is there in your laptop, okay, and what is there in many of the the Tesla cars, the electric vehicles. Those are all lithium-ion battery based. Okay, so that's really, and these are all rechargeable. Obviously, you cannot uh, chuck them away after a single use. It would never be viable. Right? So that's what it is. Now let's just try and understand one of those. One of the primary batteries. Okay, the zinc care battery. Now this is very interesting battery. Okay, which has zinc as one of the electrodes. Okay, the other electrode I think is some other metallic thing over which you are actually passing oxygen. Now you don't realize, it's very interesting. There is a membrane, a PTFE membrane in this, which is such that it just allows oxygen from the atmosphere to diffuse into the battery, but doesn't allow anything from the battery to come out, and so the cell reactions, the half cell reactions are this. It's an alkaline battery. Okay, so Zn reacts with hydroxide ion. It forms initially ZnOH4 2 minus plus gives off 2 electrons, and the voltage for this is given. It's minus 1.25 volt, which means that the reverse reaction, if I went this way, okay, it would be a different voltage. Okay, and then uh, this ZnOH4, it actually decomposes to zinc oxide, okay, plus H2O, okay, and plus 2OH minus, okay. And then at the cathode, what happens is that oxygen reacts with water plus 2 electrons, these 2 electrons, okay, and it ends up forming 2OH minus. Okay, that's what is being formed. Okay, and so the overall reaction is really that I can write it as you'll find that you got two OHs, OH minus here. There are two OH minus generated here, so that is 4 OH minus. Okay, on this side, and this 4 OH minus on the left hand side. So these will cancel out. Okay, so I'll end up getting, and so my reaction would be 2Zn plus O2, okay, over here is effectively going to 2 ZnO. So that's what I'm getting. So I just add these things up. 1.25 plus 0.34 will be equal to 1.59. And zinc, of course, going to Zn2 plus would be the preferred reaction, as we saw from the voltaic pipe. Okay, and so this is the zinc care battery, but it's a disposable battery. You cannot reuse it because there's no way of converting zinc oxide back into Zn. So you use it, it's a great battery, but then you have to chuck it away. Now, and as we discussed in the beginning, all right, this would be a typical way in which you might want to represent the performance of the zinc care battery in terms of what is the specific energy density, this, that. I might ask you, that, what do these, some of these terms mean and things like that. So you can actually figure out, okay, about something about this battery. Let me take, another battery, which is, this is actually, I will say, the forerunner to the lithium-ion battery, and a great invention made by the Matsushita company. What they did, they were the first people who realized that, if you look at batteries only in aqueous medium, that they will really have only a limited voltage. You cannot get anything more than that, because there will always be electrode reactions which will convert water into oxygen, hydrogen, and things like that, and that will be the constraint. Whereas if I use certain organic solvents, I get a much bigger pH window, not pH window, voltage window, redox potential window. Okay, And so what they started experimenting with is organic solvents, okay, and they also realized that lithium is the most electro positive element. That is, lithium loves to become lithium ion, Li plus, you know, and give off its electron. It has got the highest cell potential, you know, for the oxidation potential. Okay? Something like close to 3.5 volts or thereabout. Okay? So what they did was a very interesting construction of the cell. Okay? And you know, they took lithium as the anode, okay, a lithium metal. Okay? They had an organic solvent in which they were able to find certain electrolytes, you know, which would dissolve in that organic solvent. Okay? And at the cathode, what they did was very interesting. They took graphite, okay, which is used conventionally as a electrode material, but that's not what they did. You know, they fluorinated the graphite. Okay? So they made it something like CFN. Okay, and why did they do that? Because the reaction that they were aiming for was that at the anode, lithium will become lithium plus, which it did. Okay? And at the cathode, the electron actually came here. Okay? And what it did was that it initially formed, like it became negatively charged because that electron came to the cathode. It will become like CFN minus charge. Okay, and so this lithium, which became lithium ion, you know, will obviously tend to go towards the cathode, and it will form something like this kind of a compound. Okay, but the interesting thing is that once the electron gets pumped into this fluoridated graphite, the fluoride comes out. Why? Because fluorine is always wanting to stay as F minus. It's the most electronegative element, you know. So effectively, what they did was they took the most electropositive element known, which is lithium, and the most electronegative element known, which is fluorine, you know. And what they did was that they effectively ended up from here converting this back into carbon, the graphite, and lithium fluoride. And so the real driving force for this particular battery really was coming because of the tremendous stabilization they got from formation of lithium fluoride. And so that is what was driving their battery. Okay, but this battery, of course, after a certain time, it was it went dead, you know, because there's no way to convert this back into this and this, you know, which you have to do if you want to make it rechargeable. Okay, so you know, that was not possible. So this was a primary battery, what we discussed. Okay, but this is not something that became very popular. But let me tell you that it is this concept which subsequently was used by others, you know, and in making what is known as the lithium ion battery. uh, and in a way, I feel it's a shame that these people did not get the Nobel Prize. I mean, I actually find their work to be more interesting in some ways. Okay, now there's another great thing about this battery which you must understand, and which all of us would love to see. uh, you see, you don't want your battery to slowly deteriorate. No, what you want is it should be almost like an ideal life. You know, what is an ideal life? I mean, like you're having a you're doing all your studies, job, this, that, having a great life. You know, and then while you're at the peak of your happiness, you know, and suddenly one day you're dead. Okay? So,
Yes,
you
sir.
know, that is what an ideal battery is also. That the battery should have a flat performance, you know, from start to finish. Okay, it's having a great run, and when it dies, it suddenly dies. Okay, that in a way is the best thing, best performance of a battery. Okay, and that's what this particular battery enabled want to achieve. And so it was a great achievement. The other thing was that they could get a very high voltage. All other batteries, typically gave voltage output of around 2 volts. This was the first time when you can see they touched something like 3 volts. They were able to get something like 3 volts out of this battery, which was unheard of. So, it was extremely important. The other, of course, very important reason is because lithium is a very light element. So, I don't need much weight of lithium to make this battery. And you can see over here also, he's fluorinated it. So, fairly light element is there, which is fluorine, even in the cathode. Now, one point which I should mention over here, uh, we talked about many considerations, but let me put another one in, which is extremely important, is safety of battery. Okay, this is a extremely important thing, which is another criteria that should be used to actually assess, between different types of batteries. Okay, now let me come to what really has been one of the greatest inventions, and the lead acid battery was invented in 1859. Okay, and you can see that it has all lasted 160 years and it's still going strong. Let me tell you, with all the talk about lithium-ion battery, let us not forget that the lead acid batteries even today has a huge role to play in most of our vehicles and things like that. Solar setups, many of them, it's not lithium-ion battery, it's all lead acid battery. Okay, so so it's very important. Let us look at. You can straight away figure out what is not good about it. That is the atomic weight. It's a very heavy battery because of lead. Okay? And on the other hand, just compare with lithium, which has an atomic weight of 7. Okay? So you can see what a massive difference there is in terms of weight. Okay? But what is the reaction that takes place in a lead acid battery when you are discharging the battery? Okay, lead is reacting with electrolyte is sulfuric acid in a lead acid battery. Is reacting with the sulfate in the sulfuric acid. Okay, and it is getting converted, okay, into lead sulfate, and it is giving off 2 electrons. Okay, so it becomes Pb2 plus 2e, and Pb2 plus, and this becomes PbSO4, and you get 2 electrons, and the potential for that is 0.356 volt, as I've written it. Now, in the cathode, what is happening is that you take lead. Over here, the lead was in the 0 oxidation state. Here, you take lead oxide, which means lead is in the +4 oxidation state. Okay? And that reacts with sulfate plus the water and the electron which it got from the anode side. Okay? And it gets converted into lead sulfate plus water. And the potential for that, the half cell potential, is 1.68 volts. Okay? So if you add these two equations up, the electron over here on the RHS and electron over here on the LHS will cancel out. Okay, so they will be gone. Okay? And so what will I be left with? I will get Pb plus PbO2 plus H2SO4. Okay, all right. Plus this two oxygens from here, and again protons from here. Okay, and it will effectively end up forming 2H2O. Okay, so that's how the 4H plus and this O2 became H2O, 2H2O. Okay, and this became PbSO4, and this is this. Okay, so so that's really what it is, and you can also see that the sulfate here plus the sulfate here, that becomes two sulfates, plus you have got 4H plus, so it is like 2H2SO4. So I've got Pb plus PbO2 plus 2H2SO4 got converted into 2 PbSO4. Here also PbSO4, here also PbSO4. 2 PbSO4 plus 2H2O. Okay, and so the potential for this is I just have to add up these two equations the way I've written it. Okay, and that comes to 2.04 volt. And as I said, I mean this battery is still going strong. Okay, now this was one of the earliest, if not the earliest example of a rechargeable battery. That's why lead acid battery became so famous. You didn't have to throw it away. You could use it over and over again. Okay, so let's, I've already gone through the equations. This is for the, this is for the discharge cycle. So you can see just like last time, lead and PbO2. PbO2 is in your cathode, okay, and your positive terminal, and Pb is in your negative terminal. Electron flows from the negative terminal to the positive terminal, okay, and that's what you have, right? And you are ending up really, discharging this, okay. Now, what you can also see something very interesting is that sulfuric acid, is getting consumed in the form of it's becoming lead sulfate, and it is forming H2O, which means that the concentration of my sulfuric acid in the electrolyte will keep going down as my battery is getting discharged. Okay, and so earlier days, if you had a problem with your battery, they would first measure the density of your electrolyte, and if it is too low, they would say no, it has to go for charging. Your battery has got discharged, and there's very little sulfuric acid there. uh, and so that's really what they have to drain out the electrolyte completely and put in fresh sulfuric acid. When you do the recharging of the battery, all you're doing is you're connecting it up in the reverse direction. Okay, so now basically what will happen is my current, instead of flowing from this direction to this, okay, my current is actually flowing from this direction to this, okay, because my lead sulfate which had formed here has to be reconverted back into lead oxide, and in the other side my lead sulfate has to get reconverted into lead. Means over here I have to reduce, so I have to receive electrons here, and over here I have to oxidize my lead sulfate to lead oxide, lead dioxide, so I have to do an oxidation. So this now becomes effectively my negative pole at the time that I'm doing recharging of the battery, and this will become my positive pole. Okay, so the poles will get reversed, when I'm doing a recharging, and exactly the reverse reaction will happen. Okay, what will happen is now your water will get converted back in, and the sulfate in the lead sulfate will get converted back into H2SO4 during recharging. Okay, you can look at the these reactions. It's quite simple. All right. So this is really how the lead acid battery gets discharged, and it can be recharged. And that's what made it. And it can be completely recharged. I mean, it's and you have. I mean, till this lithium-ion battery came around, this was one of the best batteries anyone could use. Okay, I will discuss these later on when I'm comparing with the lithium-ion battery, so I won't go through it now. Now, there's another thing that you must remember is that in this lead acid battery, what happens is that what did we say? As it is getting discharged, the sulfuric acid is getting consumed. Okay, so my concentrations of the ions in the solution is changing. Okay? So by Nernst equation, there will be an effect on the potential. So my potential will not remain constant. Unlike in like this case, where we said it's absolutely constant and then suddenly it falls off. Over here it will continuously change. Okay. Now that is given by this equation, okay, where basically the potential at a given time, okay, the EMF will be dependent on how many cells you have connected in series. That is the number of cells in your battery. Okay, and each cell, we had seen is about around 2.15 volt is the potential, and minus what this is it's called the depth of discharge. Okay, what it means is that suppose my battery has got discharged 30%. Okay? So, okay, so I'll call my depth of discharge as 0.3. Okay, so I'll multiply that with 2.15, which is the voltage of my cell minus 2. Don't worry about this equation. Okay, and so you can see that this term will be obviously positive, 0.15, and so this term will be negative. Okay, and so I'll have to subtract it from 2.15. What it means is that my voltage will keep dropping, okay, as my battery is getting discharged. Okay? That's what this equation says. Okay, let's look at another rechargeable battery, which is the nickel cadmium battery. Now, which has very interesting properties. So unlike in this particular case, where the voltage is keeping on reducing as my battery is getting discharged, in this particular case the battery voltage remains flat, like in the other case that we discussed. It is like the best way to die. Live a great life and then suddenly you're gone. And so let's look at the nickel cadmium battery. You must have heard the name NiCad. NiCad battery is this nickel cadmium. Okay, so in discharge, what happens is that cadmium gets oxidized to cadmium 2 plus. Okay, and it reacts with hydroxide. So quite similar to the zinc air battery that we had seen. It becomes cadmium hydroxide and it releases 2 electrons. Okay, and the voltage for this reaction, as I have shown it, is 0.82 volt. Okay, that's the oxidation potential. Okay, and at the cathode, I've got nickel oxide hydroxide. So the oxidation state of nickel is actually +3. Two, this oxygen will be -2, and the hydroxide will be -1. So it overall total will be -3. So it's counterbalanced by a charge of nickel +3. Okay, so this plus H2O plus electron, which it gets from here, so it will become nickel hydroxide, means it got reduced from nickel 3 state to nickel 2 state. This is nickel +2 and this is nickel +3. Okay, and what it does is that it releases hydroxide. Now, since there is 1 electron here and 2 electrons are produced here, so actually I need to multiply this by 2. Okay, so so it will become 2 NiOH plus 2 H2O plus 2E going to this. Remember, your voltage just does not change when you change the stoichiometry. Okay, it will show up in the free energy of the reaction. It will show up in delta G is equal to minus NFE. There it will show up. is as N, but your voltage does not change. If I multiply this by 2, the voltage will remain the same. Okay, and so I can add these two up. It will become 1.42 volt. Okay, and the net reaction will be cadmium sulfide plus 2 of this plus 2 of water, because I multiplied this equation by 2, will become cadmium hydroxide plus 2 of this. Okay, and my electron will cancel out. Okay, that's what it happens. Okay, in this. All right. So that's the reaction. Okay, in this particular case. Okay, and now yeah. Now, in this particular case, okay, what happens is that when don't worry about what I've written over here, okay. Um, um, uh, just remember the recharging, okay. Recharging means I'll exactly go in the reverse direction. That is, cadmium hydroxide will again get converted into cadmium, okay, and nickel hydroxide will get converted into nickel oxy hydroxide. Okay, so I'll have to flow my, I have to bias my elect cell in the opposite direction, so that my positive pole becomes my negative pole, and my negative pole becomes my positive pole at the time of recharging. Okay, so that's basically the nickel cadmium rechargeable battery. Now, in case I ask you, I mean, let's do a quick sum, all right, so that a current of 2.75 ampere is measured during recharging of a nickel cadmium battery. Recharging means I'm going in this direction, right, carrying out this reaction. Okay, and so what he says is that with an external potential of 2 volt, I'm applying a voltage higher than this. Obviously, I have to apply a voltage higher than the cell potential. Okay, and typically you will apply a voltage still higher than that, because you have to overcome cell resistances, and there's also something known as over potential. That means the higher is the net difference in the voltage between the amount that you're putting in and the amount that is required. That provides the driving force for the reaction, and so more current will pass, and you can do your recharging faster. Okay? So what it's asking you is that how many moles of cadmium will be redeposited after 5 minutes of charging. Okay? Cadmium hydroxide is becoming cadmium. Okay? So time is 5 minutes. So I have to convert it into seconds. So 5 into 60. Okay, so many seconds. And what is the current that was passed? 2.75 ampere. Okay, so my total coulombs, which I have passed, okay, will be equal to, all right, this much, 5 into 60 into 2.75. That will be my total coulombs. Coulombs is equal to ampere second. Okay, and now what I have to do is that I have to divide by Faraday. Faraday is the number of coulombs that you need to pass, okay, for 1 mole of charge. Okay, so per mole of charge, per mole of electron. Okay? So when I do this, my basically my coulomb over here cancels out with this coulomb in the denominator, and my per mole in my denominator will become mole. So I'll end up getting, you can do the calculation, it'll come to 0.00855 mole. So this basically tells you the total moles of electron which have actually passed when I did this charging. Okay? Now, for each of this reduction of cadmium hydroxide to cadmium, I need 2 electrons. Okay? 2 electrons are required. So when this went in, I'm going in the reverse direction. So I need cadmium hydroxide plus 2 electrons to go back to cadmium. Okay? So effectively, that what Faraday's law tells you, all right, is that you have to now divide by the number of electrons, which is what is the equivalent weight. Okay, and so effectively, the number of moles of cadmium which will deposit is actually equal to the total number of moles of current that I passed multiplied by half, because only half of that will be cadmium, because I need 2 electrons per molecule of cadmium hydroxide going to cadmium. Okay, so the actual moles of cadmium which will deposit is half of this value, right, which is half into this, which is 0.00428. Okay, so this first equation enabled me to calculate total moles of electron which were passed when I was recharging my battery for 5 minutes at a current of 2.75 ampere. Okay, and this one basically tells me that the actual amount of cadmium that will deposit will be half of that, because 2 electrons are required per molecule or per mole of cadmium. Okay, is that clear to everyone?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, now let us come to the lithium ion battery. These are the three people who won the Nobel Prize, in 2019. Okay? And the work really was pioneered by this gentleman, Stanley Whittingham, who was a Britisher, but then later on he shifted to the US. He's also a Britisher, John Goodenough, who again migrated to the US, later on. Okay, and in Japan, this person, Yoshino, okay? He was working in a company. Okay, I think it was Asahi, if I'm not mistaken. But so these are the three people who shared the Nobel Prize. But when I look at the contributions of many others, and I told you about the Matsushita company who made the first lithium battery. Okay, then Sanyo company, they were Sony company, did huge amount of work and were actually the first to commercialize the lithium-ion battery. And another person called uh, Richard Yazami, and these are all people, gradually people forget, okay, and people only remember these people. But I just thought that I'll pay my tribute to these people also, because I feel that they were also very worthy and made extremely important contributions. Okay. So let us try and understand why is it that they got the Nobel Prize? Why all this fuss about the lithium-ion battery? Okay. Now look at the story of the lithium-ion battery. That even in around 2016, you can see that it's nothing, in terms of how much it contributed to gigawatt hour of storage. Okay, and now we are in 21. Okay, so we are here. Okay, and you can see what we think is a huge thing, because all mobiles today use the lithium ion battery, but still you can see that it is considered to be low. And what people think is that by 2030, which is another 9 years from now, this is where it will go. Okay, and so it's a massive surge in the requirement for lithium-ion battery. Uh, why there's going to be such a large requirement is because now everybody is talking about electric vehicles. Now, obviously, you can understand that compared to a mobile, your car will require a much bigger battery, right? And so, and imagine the number of cars. It contributes 30% to global emission, vehicular traffic. So, if all those have to change over to lithium-ion battery, then of course it's going to be sizable. The question then is, why do people want to change over to the lithium-ion battery from whatever exists? The reason is Very simply because the lithium ion battery offers many advantages. One of the most important being that it is much lighter than the lead acid battery. So with the lead acid battery, you're carrying a lot of dead weight around, which will not happen with the lithium-ion battery. Okay? And of course, there are many other reasons which I will touch upon as I go along. Now, so I just thought, just so that you can understand from a simple layman's point of view. So he's not a scientist; he's a writer, okay? And so he writes, for certain magazines and all. And I just thought it's interesting to what does a person like him think about the lead acid battery. And he was asked what are the main types of battery in use today and how are they different. So what is his understanding? And he says there are two main kinds of batteries you all probably will be familiar with: the lithium ion batteries power things like our phones and electric or hybrid vehicles, and lead acid batteries that are used to start cars with internal combustion engines. That's what we all have, the ones with the petrol engines, okay, and store power for the cars, lights, radios, and other devices. So these are the two, and you can see you have learnt about the lead acid battery. Now you're going to learn about the lithium ion battery. And then he brings out why it is important. The main difference is the energy density. Remember energy density, okay, which we talked about, okay. And actually, what he is talking about is specific energy, not so much about specific energy is the energy per kilogram. But many of these people use it interchangeably. When you say energy density, technically it means per unit volume. Okay, and what he says is you can put more energy into a lithium-ion battery than lead-acid batteries, and they last much longer. That's why lithium-ion batteries are used in so many applications and are replacing lead-acid batteries for things like transport and grid applications. So this is going to be a huge transformation, from the lead acid battery. And another reason, of course, is that lead is not is considered to be a toxic element. So that's also another reason why it's going out of favor. That people would prefer things which are lead free. Okay? Okay, and where it matters so much, the main difference is the energy density, and you can put more energy into a lithium-ion battery. And I've shown you this before once, okay? And this plane that I told you is flying entirely on solar energy, okay? And during the daytime, it is all these photovoltaic panels, which are powering the plane. But this plane also over here contains batteries, okay. And in fact the main weight beyond this and one pilot is really the weight of the batteries. And imagine if you had to put lead acid battery, this plane would never fly. It would just be sitting on the ground. It would be so heavy, okay? But with the lithium ion battery, what happens is that during the daytime there is sufficient power that is generated, that not only does it fly the plane during the daytime, but it also continuously stores, and recharges the lithium-ion battery. And at night, when everything is dark, okay, this plane is flying, but flying only out of the lithium-ion battery. Okay, so in darkness, that's what is happening. And so this plane has literally flown, at non-stop for 5 days, non-stop, without anything, because there's not a gram of fuel anywhere. Okay? So it crossed the Pacific Ocean, with not a gram of fuel put in. Okay, so so both played a huge role. One was the photovoltaic cells. You have learnt about the photovoltaic cells, and you've learnt about the lithium-ion battery, or you're learning now. And these photovoltaic cells, by the way, are of a special design. They're extremely lightweight. They're very, very thin. So it is not like the photovoltaic cells which we might have in our rooftops and things like that. It's a much, much thinner cell, okay, specially designed. Okay, now just to also tell you that how seriously everybody is considering lithium-ion battery. Uh, this, of course, may change now, but this is an article from 5th February 2021, where what you can see is Suzuki, Toshiba, and Denso to make Gujarat lithium-ion unit, okay, an export hub. Okay, we are talking about the major Japanese companies, wanting to come here, okay, and to set up lithium-ion battery manufacture. Okay, so that's the kind of thing that we are talking about. Okay, obviously, a lot of emphasis on the lithium-ion battery. Okay, now let me take you through the lithium-ion battery has gone through a few developments. Okay? And the first development I told you was Matsushita, who did not make a rechargeable battery. They made a primary cell, but out of lithium. And let me tell you, I mean, I find that 80% of the ideas uh, by all these Nobel laureates, they borrowed from Matsushita. I mean, yeah, they also did great work, but Matsushita actually made huge contributions. Okay, so this is the first, what they did was they, the first great thing that they were able to do was that they were able to make the lithium battery rechargeable. Whereas Matsushita's battery was primary cell. You could not recharge it. These people were able to make a rechargeable lithium battery. Okay, and what is the basic reaction that is taking place? Uh, when they started, they took a lithium anode, just like Matsushita had done. Okay? But the cathode which they took, in this particular case, was a metal oxide, and it had a very unique property that lithium could go into this metal oxide, and also it could come out of this lithium metal oxide, depending on the at what potential you bias that electrode. Okay, whereas in the Matsushita case, in this case, you see the electrode, once it had taken up the lithium and the electron, it dissociated and formed lithium fluoride, which cannot be reversed. So that's why this was a primary cell. You could not recharge it. Whereas with this particular cathode, this one, it was possible to not only put the lithium in, but you could also, lithium said, yeah, I'm happy to go in, I'm happy to come out, depending on the potential that it sees. Okay, and so that is what made it possible. And likewise, the lithium which formed a lithium ion at the anode, they were able to convert it back into lithium metal. And so that was a huge development that took place. Okay, now that was done by this person, Stanley Whittingham, and it happened in the 70s. In fact, this you can see is a cell from 1977, okay, which he had made. He was working at the Exxon company, okay, and of course he had done his PhD in Oxford, and then went to Stanford, and that's where he picked up all this wonderful knowledge, and partly from his professors and partly he contributed. Okay, and so he made initially not an oxide but this kind of compound. It was a titanium sulfide, TiS2. Okay, but these are solid state materials, they are not single molecules. Okay, so when I say TiS2, I don't mean a molecule of TiS2. Okay, they are, it's only the overall composition written that way, but they exist in these kinds of structures, layered structures. And what he was able to show is that if he applies a bias, a potential to this electrode, the lithiums get in, and if he reverses the potential, the lithiums go out. And he said, this is wonderful that I can get lithiums to come in and go out. Okay, and so and as I said, I mean that is what really led to the formation of the first lithium ion battery. Okay, but where the anode was lithium metal. Now, did I? Yeah, the anode used was metallic lithium. Okay. Now I'll put something which I forgot to put here because I might forget later on. When Li plus is reconverted to Li during charging, the morphology of the electrode changes and there is dendrimer formation. This I came to know from the Nobel lecture of John Goodenough, the other person, and this can pose problems such as short circuit. Because these dendrimers, like I started with a nice smooth lithium electrode, but it dissolved, it became lithium ion, and then again they are reforming the lithium. But now the lithium does not form as these flat sheets of lithium. What happens is it forms like whiskers. There will be many, many thin wire-like lithium that will form, and it will protrude out, and it can go and short circuit the cell. I mean, that lithium can go and puncture the cathode, and so you can have an explosion. So those were the problems, with the lithium metal. But I just thought I'll put it down. Okay. Then came this man, John Goodenough. By the way, John Goodenough is the oldest Nobel laureate to have got the Nobel Prize. He got it at the age of 97. Okay, and so this what he did was uh, although Whittingham was able to make the lithium battery, but it did not serve its primary purpose. The primary purpose was to get a high voltage out of your battery. And what they found is that the best that they could achieve was around 2.5 volt. I mean, maybe a marginal improvement over the lead acid battery voltage, but nothing more than that. Okay, and so what Goodenough did was he studied the problem that why is it that it has a low voltage, and he realized that it is because of the nature of this material titanium sulfide, that the kind of electronic states, the bonding and anti-bonding electronic states are such that that is what constrains the potential. Okay, I'll try to explain it better in the one of the future slides. Okay, so what he did was he kept experimenting with other electrodes, and found that he could make certain metal cobalt oxide kind of compounds, which are again layered materials like this. And those also could, the cobalt, the lithium could come in and go out. So this is what he was able to do. This person good enough, and he was able to raise, the voltage 3.5 to 4 volt, uh, by changing over from the titanium sulfide layered material, to a cobalt oxide layered material. Okay, it was still layered like this, and the lithium ions could get in and out, but it offered a much higher voltage. Okay, uh, now so that was a huge jump, which happened. Okay, in this, their entire focus was on the cathode, and they were able to design the cathode quite appropriately, and raise the overall cell potential to something like 4 volt from 2.5 volt, which Stanley Whittingham had achieved. But the problem was that the lithium anode was still a lithium bare metal. Okay? But this person, one person called Yazami, had done some work where he was able to show that, just like those cobalt oxide and titanium sulfide, that graphite also has a very interesting property where lithium can go in and out. And so, this was something which provided the inspiration for a subsequent work, which was done by the third person who got the Nobel Prize. But at some point, this person, Yoshino, he said that, oh, this is wonderful. If we can have a system where lithium ions can do this kind of trick both at the anode and the cathode, that is, it just goes in and comes out, and then, I don't have to form lithium metal. Okay, that was the thinking. But then when he did the experiments with graphite, what he found is that graphite is not a suitable electrode. I mean, it does do what Yazami had talked about, that lithium goes in and out. But the problem is that I did not mention to you that there is a third component, in a cell. I need electrodes, and I also need an electrolyte. Okay, and that electrolyte is a non-aqueous electrolyte. I'll show you what kind of things are used. Okay, into which some lithium salts have to be dissolved. Okay, so that is my electrolyte. Otherwise, there will be no conduction pathway, no ionic conductivity possible in the cell. Okay? But the problem was that those solvents which are used in the electrolyte, they went and attacked the graphite. When all the cycling of the electrode was taking place, and slowly, it was getting all absorbed in that graphite, and the cell was getting dry. And so it was not feasible. Okay? One is that you can make a complete U-turn and say, let me work on some other material which is not carbon. When you are confronted with a problem, you don't have to make a complete U-turn. Yoshino, what he did was, he stuck to carbon, and he started playing with different types of carbon. All kinds of carbon he started making. And in particular, he started varying the density of the carbon. Okay? And so you can see this is the density axis, and this is known as the lattice parameter. Don't worry about what it is. Okay, but what is interesting is that ultimately he was able to come up with a carbon at a particular density, which really was wonderful, in the sense that it did not get attacked by the electrolyte, by the solvents in the electrolyte. Okay, so I'll just read out what it says here. As carbonization proceeds, the structure becomes more similar to that of graphite. graphite was unusable because it reacts with propylene carbonate. This is the solvent. This caused the electrolyte solution to decompose, generating gas. This gas accumulated between layers of active material, causing electrolyte solution to dry up. The layers of graphite would also break up, resulting in severe battery deterioration. Okay, so effectively, what Yoshino was able to do was just like Whittingham and Goodenough, they were able to develop the required cathode. You know, Yoshino was able to develop the right anode. Again, a carbon-based anode, but the right anode. And so you can see, by the way, this is the relationship between research and technology. In technology, you are confronted with a problem, and then somebody has to sit down and analyze the problem and get to the heart of it, and then try to solve it. Okay, so that's what Yoshino was able to do. Okay, so let us now look at what really is the reactions that are taking place, in the lithium-ion battery. You can think of this as the discharge state of the two electrodes. Okay, in the metal oxide, the cathode, it is like as if there is one lithium, one cobalt, and two oxygens. So two oxygens will have a total negative charge of -4. -2 into 2, -4. Cobalt, lithium has a charge of +1. So cobalt is +3. Okay. So this is like as if this material is a cobalt +3 material. Okay. And in my other anode, okay, I have got just a pure carbon. That's what I have. Now what I'm doing is I'm pumping electrons, from this side to this side. Okay. So what is therefore happening? Some of the cobalt will become from +3, it will go to +4. Okay. It will start moving towards +4. Okay. Now when it does that, the electrons flow into this negative electrode over here. Okay. And it starts getting a negative charge. It becomes carbon minus. Now, when this becomes more +4, it loses its affinity for this lithium because it's not required. So a part of the lithium actually migrates out and it comes to the carbon, which has started picking up a negative charge. And so it now starts looking like this. Carbon as if it's got a negative charge, and it is counterbalanced by these lithium ions. And these lithium ions came from where? It came from here. Okay. And so to that extent, there was a drop of lithium ion by X, and now the new amount is lithium 1 minus X. So it is as if some of the cobalt is in the +3 state and some of it is in the +4 state. Okay, that's effectively what it means. Now, if you remember, I was trying to show you here a +3 +4 state, and you can see what is written. Okay, so that's exactly what is happening. So, electrons are being pushed out of the +3, cobalt +3 state, and that is what is reducing the graphite over here. Okay, and it is because of this that you get such a high voltage. Okay, now, so that is the charging and the discharging of the lithium-ion battery. Now, so you can pictorially show it. Okay, like this is my my graphite. Okay, my graphite type of material. You can see 6-membered rings. Okay, and there is lithium ions here. Okay, and this is my cobalt oxide. Okay, so there is some lithium ions here also, and the lithium ions are just shuttling back and forth between these two electrodes during the charging and discharging. Okay. Now, this is what it is. Like, this is the place, right, where my, let's say, my carbon electrode with some lithium is somewhere here. This is the occupied orbitals, okay, and this is my cathode, okay, where after it has lost its some of its electrons, the cobalt, it is more like a cobalt +4. It is buried deep down, okay, and you can see the difference between these two lines is basically my cell potential. Okay, that's what the cell potential is. Okay, so this is my graphite or carbon with some lithium, and then electrons are flowing from here and it's coming here, and I'm talking about the discharge cycle. When I go to the charging cycle, I do exactly the reverse. I have to push this up and this down. Okay, that's effectively what I do in the charging cycle. Okay. Now, this is the electrolyte. Okay. You need electrolyte as well, not just the electrodes. Okay. So this is propylene carbonate, these solvents. Okay. And these are some lithium compounds like lithium hexafluorophosphate. Okay. Which is what gives you ionic conductivity in this lithium ion cell. So this entire electrode is all about a dance of lithium from one end to the other end and back again from this end to this end. That's what it is. And how to keep the structure stable so that it doesn't react with the solvents. Okay, solvents do their job of imparting ionic conductivity, right? But other than that, the solvents do not react with either the anode or the cathode, and that's what keeps it stable. Okay, and also another very important thing is that the cell resistance has been minimized, by the kind of solvents, etc., that have been taken. Now, let me tell you about two more significant things that Yoshino did apart from basically inventing this particular kind of carbon, which had this fantastic property. One was Yoshino realized that if he just takes this cobalt oxide and this graphite or this carbon and the graphite cobalt oxide, that there is too much of resistance in the cell. So he took some metals, like aluminium and copper, okay, and he coated the stuff on these. So these were actually my primary electrodes, these metals. And with this, he was able to bring down the resistance in the cell quite significantly, okay, and basically he calls those as current collectors. They're just metal pieces on which these stuff are coated. So that was one. The second very interesting thing was that there was still a fear that suppose, for example, some lithium, let's say, although we are writing the structure, there could be presence and formation of some amount of lithium metal, and or let's say there's some short circuiting and the temperature shoots up, in my cell, and then there can be an explosion. So what he did was he introduced the concept of a polymer fuse. Okay? And so, this stuff is nothing but a porous polymer, porous polyethylene. Okay. And, when everything is fine, this thing is just sitting somewhere, let's say, in between the anode and the cathode. Okay. And it has no role to play. It's just, and it's so porous that everything just passes through. There's absolutely no problem. Okay. But the moment if there is some overheating, some short circuiting, then because polyethylene has a low melting temperature, it melts and it blocks off all these pores. Okay? And it becomes then just like a sheet of polymer with no porosity. Moment there is no porosity, there is no pathway for the lithium ions to move back and forth. So automatically it cuts off the cell. Okay, And that's basically how he was able to make the lithium-ion battery very safe. You know that the Samsung batteries at one time used to have a problem, and in fact they banned it from aeroplanes. But this person was able to overcome, the problem with this kind of a polymer fuse. Okay, just to show you a comparison of why lithium-ion battery has become so important, okay, I've compared the lead-acid battery and the lithium-ion battery. Take specific energy, 20 to 35 watt-hour per kilogram. Over here, 90 watt-hour per kilogram. Energy density per volume, 54 to 95, 153. Specific power is not very different for the two, although over here it is marginally higher. Specific power, okay, yeah, which we said is watts per kilogram, at an instant that you can draw. The nominal cell voltage, 2 volt, here is 3.5 volt. So you get not only a large current, but you get a huge potential, and that's why the wattage is so high, in this lithium-ion battery. Okay. Now, the ampere-hour efficiency is comparable, very good in all the cases. The internal resistance, because this would be a loss, and also it will lead to heating up of the cell if your resistance is high. It's very low here, okay, and also very low here. I don't think there is much of a gain in terms of internal resistance. Okay. Commercially available, yes. Today they are commercially available, at least for mobiles and things. For electric vehicles, not really, because they are way too costly at present, compared to the lead acid batteries. Okay. Operating temperature of both are ambient. Okay. The self discharge, you remember that if you are not using your battery, what will happen? Over here in the lead acid battery, every day you lose about 2%. So if you come back after a month or a month and a half, there's nothing, your battery is dead. Okay? Over here, it is as low as 10% in a month. So even if you come back after 2 months, chances are that your battery will be running. Okay. The number of life cycles, how many times can you charge and discharge, it's somewhat better with the lithium-ion battery, greater than 1,000. Okay. And this is very important, like if your battery has gone dead, how long will it take you to recharge? Like sometimes, you are sitting in the airport and your battery has gone dead, there are chargers, but you hardly have 15 minutes of time before you're boarding the flight, and you can't do anything about it. Okay? Now, lead acid battery takes 8 hours to recharge. Okay, whereas lithium-ion battery, in a couple of hours, you can more or less get at least some charge. So there are huge advantages, okay? And this is the reason why the lithium-ion battery, is increasingly being talked about. But as of today, the lithium-ion battery is certainly much costlier than the lead-acid battery. So that has to be taken into account, and the safety, etc., will need to be also taken into account. Okay, the final thing about the lithium-ion battery, which makes it a great invention, and again, I think something which was done by Yoshino. You see, what happened was, let me ask you this question. Between this and this, which is more stable pair, which is the more stable state between these two?
So the discharge state.
Wonderful. Wonderful. Okay. So what basically this person did, was said why do I have to assemble the battery in a charged state? You see, this is very interesting, and you must be able to think like this. Most of the concepts in battery came from the primary cell. Primary cell has to be charged because it can be only a once off use, right? It has to be a fully charged battery. But that is not true in a rechargeable battery. Okay? So what Yoshino said, I hope it's Yoshino and not somebody else. I'm not very sure. I think it was Yoshino. What they said is that why don't we assemble the battery in the more stable discharge state? And then once the battery has been assembled, at that time, I don't have to take any safety precautions or minimal safety precautions, and it says over here that achievement of a simple and efficient production process with no special atmosphere required for battery assembly made possible because LiCOO2 is very stable in air. That is the discharge state despite containing lithium ions, and the negative electrode is composed of carbonaceous material, which is also stable. So this state was stable. They did not have to, take any special precautions. So they assembled the battery and then they charged it. I hope you can see, how brilliant it was, and so it became extremely easy, and mass production could actually be carried out because of this very simple concept. Okay, uh, two other things which I want you to know, because before we close on battery, okay, is that firstly let me tell you that there is a big problem once your battery goes dead. Okay, and most of the people I've seen, their previous mobile, the one before that, is just lying in your house. But if you really had to dispose of it, you know, the battery would be treated as a hazardous material. Nobody will allow you to just discharge this battery just like that. And secondly, there is, like, India does not have any source of lithium, very negligible source. So, for us, the billion telephones, mobiles which are there and where the battery is going to go dead, these can become, or your laptop, so many laptops, these can become your source for lithium. Okay, so recovering the elements from the discarded battery is a huge thrust area today, both from the angle of environment, just so that its discharge is safe, and also from a resource angle, because cobalt, for example, is a very costly element, and so it would be nice to be able to recover the cobalt, right? So that's what you can do, and this is the area where a lot of work is going on. Second, let me tell you, while you saw that projection of by 2030, what will be the volume of lithium-ion battery, let me tell you, a lot of work is going on in other batteries. Like, instead of lithium battery, people are working on the sodium battery. People are working on a fluoride battery. Okay? And so don't be surprised if in 10 years time, lithium-ion battery is a thing of the past. And you'll talk about lithium-ion battery and someone else will say, what lithium-ion battery? Really? You had something like that? So, the situation could change quite a bit in 10 to 20 years time. So technology never remains standstill. Okay? People will be looking for alternatives, and the reason is because lithium is more difficult to procure. Sodium is abundant. Okay. So if I can make a battery from sodium, and sodium is also got a very high oxidation potential, so I should be able to make a battery out of it, and people have. Okay? So it's a question of being able to improve it. Okay. Finally, before I end this course, okay, I just thought I will show you something which I saw in yesterday's Times of India. So I wrote it down. Okay, I thought I'll share. What does it say? Renewable power companies' dues surge 47% to rupees 21,000 crore in 1 year. Defaulting state distribution utilities may hit climate goals. So what has happened is that I've shown you data, statistics, it all looks very rosy, but you don't know what is the reality behind it. It may be all useless projects which will die. They will not survive. Okay, and you'll default on your loans. All right. So what this course is trying to teach you, okay, is also that you have seen that there are so many options for renewable energy, okay? And there are also so many limitations of renewable energy. And what we have tried to do is we have tried to cover the entire breadth, all the way from hydropower to photosynthesis to nuclear power, which I took as also renewable energy, to windmills and PV power, etc. So what you need to do is that you should be able to critically assess technologies, okay, and decide for yourself what is the best thing to do. And so that is what should be really the going forward, the kind of idea with which you should have taken this course. And even if you didn't take it with that idea, but at least you should leave the course with this kind of an idea in mind. Okay? Is that clear?
Yes, sir.
All right. So thanks a lot.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you.